Okay, so today we will wind down our study of first order differential equations. And from the next class onwards, the plan is to move on to second order differential equations. Okay. So today we want to wind down the study of first order by saying a few general things about solutions of first order differential equations in general. And I found that the best way to start this discussion is by working out a couple of simple examples. Okay, so let me start with a very simple first order differential equation that you probably know how to solve in your sleep. Okay, so let me start with an example. The example that I would do is y prime equals x times square root of y minus a, where a is some real constant. Okay, it could be positive or negative. I don't care about it. I'll fix some value of a as we go along. But right now I want to basically solve this differential equation. And you will probably laugh at me because you think this is too simple, and it is actually, right? So the way you would solve it, because this equation is easily separable. So this equation is easily separable. So I will write this as y minus a to the minus 1/2 dy equals x dx, right? And then I can go ahead and integrate this equation. And this gives me a positive square root y minus a and a half in the bottom. So that becomes 2 times square root of y minus a. The right hand side is x squared over 2 plus c. Okay, so if you want, you can clean this up further by squaring both sides, and you will have the solution. There is absolutely no problem with this, right? Okay, so now let me actually turn this into an initial value problem. Initial value problem. Okay, I will abbreviate this as IVP to avoid writing the full form every time. So what's an initial value problem? Well, this is what you have in the line above is the most general solution to this particular equation. But suppose if I give you some initial value at x is equal to, I don't know, 10 and y is just 2 or something like that, then you can fix the constant c using this particular initial value, and that gives you a particular solution for this differential equation, right? So right now we have a whole bunch of solutions with varying c's. But once you fix c by appealing to an initial value, you get a particular solution to this differential equation. So let's use the same equation. And I'll call this IVP1. This is the first initial value problem that I will do. My differential equation remains the same. Y prime equals square root of, let's say, y is a is, I don't know, 5 or 10, or whatever it is, right? Times x. And now with the proviso that y at x is equal to 0, it doesn't have to be 0, is 2 or whatever, it doesn't matter, right? So initial value problem specifies a bunch of, a pair of points, x0, y0. At the point x0, the value y0 is actually given to you. So your solution should conform to this particular point. So x0, y0 in our case is 0, comma, excuse me, I'll write it a little bigger, 0, comma 2. Okay. So can we go ahead and finish this? Of course we can, because we know that now I should simply write the solution 2 times y minus 5 equals x squared over 2 plus c. And then I will simply plug in this initial value, right? So at x is equal to 0. So let me actually make this slightly larger so I don't have imaginary numbers. So let us say y is 10. Okay. So if that is the case, then x0, y0 is for me 0, comma 10. Plugging this, I have 2 times square root of 10 minus 5 equals 0 plus c. And this fixes my c. So c is basically 2 square root of 5. That's it, done. Right? So this is how you solve this particular equation. No problem. So let's go ahead and talk about the second initial value problem. I will take the exact same differential equation. Y prime equals square root of y minus 5x. And this time I will say my initial condition is, I don't know, y at x is equal to 8 is 5. Once again, you can solve for c, and then at this point, you would probably wonder why I am boring you in the morning. But a little patience, I have a point to make. So 2 times square root of y minus 5 is again x squared over 2 plus c. But this time, my x0, y0 is 5, 8, right? And now this is even simpler because the left-hand side vanishes because at y equals 5, the left-hand side is 0. The right-hand side, of course, is 8 squared over 2, which is 64 over 2, which is 32 plus c. So this fixes c. So now you can write solution 2 times y minus 5 is x squared over 2.
The coordinates are 8, 5. That's right.
Hello, yes?
Yeah, coordinates are 8, 5.
No, it's 5, 8. So I'm telling you that y at the point
Okay,
x is equal to 8 is 5. So this notation means that y at the point x0 equals y0. Okay, so that is the notation I employ.
Yeah, so why not should be 5 now?
Where?
In down in like you have written x naught, y naught is 5, 8.
Oh, okay, here.
Yeah.
Yeah. Oh, I'm sorry. Yes, you're absolutely right. So this is 8, 5. This is what you mean?
Yeah.
Okay, thanks. So at the point x is equal to 8, the value of y is 5. So this fixes my value of c. And I can go ahead and write down the solution. But if I stare at this differential equation, I realize that since you guys already learned about singular solutions in the tutorial problem, singular solutions are those that cannot be gotten by ordinary means, right? Now I can wonder if there is any other solution I can possibly write. Okay, and the answer turns out to be yes. And even though you would not agree with me that this is really a deep solution, I can, in principle, write another solution for this initial value problem. There. Y of x equals 5. Okay. Now, you might have a hard time accepting this as a solution, but if you do, I would encourage you to go back and look at the definition of what a solution is. And this is something that we briefly touched upon during the initial lectures. Maybe if I can go back. Here it is, right? So what is a solution? A solution is simply that particular function of x, which when I substitute back in the differential equation, I get an identity. Okay, this is the definition of a solution. This is my minimalistic definition of a solution. This is what people employ. So with this definition of what a solution is, I can ask if y equals 5 is indeed a solution of this differential equation. And it turns out that it is, because if y is a constant, y prime is 0. So the left-hand side of this differential equation is 0. And if y is 5, square root of 0 is 0. So the right-hand side is also 0. So 0 equals 0 is perfectly okay. Okay. So even if you think this is a trivial solution, I would point out that this is not actually so trivial, because it is not possible to write such a constant solution for any given differential equation, for instance, right? So for example, for the exact same differential equation with this particular initial value problem, I invite you to find y equals constant solution. It is simply not possible. Okay. So for this initial value problem, for the same differential equation, this is the only solution possible. C equals 2 root 5. But for the same differential equation with a slightly altered initial value, it is possible that I can have two solutions. Admittedly, one of them is just a constant, but it's still a solution. Okay. So what's going on here? So the lesson is that depending on the initial value, the number of solutions that you can have for a particular differential equation can vary. Okay, so I'll give you another example. So I'll call this IVP3. And let me take the example of, let us say, again, a very simple example. This is from your book. This equals 1 minus y. And the initial condition is y of 0 equals 1. Okay. Again, solve this differential equation, divide out by 1 minus y and times x, and you get dy by 1 minus y equals dx by x. Integrate this trivially, and you get logarithm 1 minus y equals logarithm x plus some logarithm c, where I call this constant as logarithm c, which I can always do, which tells me that my solution is 1 minus y is cx, or y of x equals 1 plus cx. Okay. Now the question is, again, if I go forward in the exact same way, I would try to fix my c depending on what my initial conditions are. So the question is, what is the value of c that fixes this initial condition? The answer turns out to be anything. Okay, because my initial condition is x0, y0. In this case is at x is equal to 0. I said y equals 1. So substitute that. You already get 1 equals 1. It doesn't really matter what c is, because c turns out to be a multiplicative constant here, not an additive one. So at x is equal to 0, the second term really vanishes, and y, this differential equation, the way it is written, already satisfies this initial value. So what are the solutions? The solution could be anything. For any chosen value of c, this particular solution satisfies both this differential equation and the initial value. Are there any questions? Anybody?
There should be x into y minus 1 equal to some constant.
What was that?
So I think it should be x into y minus 1 is equal to some constant. The solution to that.
X into y minus 1 equals. Sure, but because I can write it like this, right? See, logarithm 1 minus y is logarithm. So I can write this.
You forgot the minus sign, I guess, in the integration of dy over 1 minus y.
Okay, 1 minus cx. You mean here?
No. In integration, ln of 1 minus y.
Yeah.
It should be ln of 1
Okay.
upon 1 minus y.
Now, are you happy?
Yeah.
Fair enough. Okay. So the point is not the particular session. Thank you for pointing out. The point is that there is always a possibility that there could be differential equations, or rather initial value problems, that could have multiple solutions. Okay. So we had one example where there is just one solution possible. We had the same differential equation with two solutions possible. Now we have a third initial value problem with multiple solutions possible. In fact, an infinite number of 1, because there is no way I can fix c. And remember that this depends on the initial condition. For example, if I change my initial condition to, I don't know, y at x is equal to 2 is 5 or something like that, right? Then this is not satisfied for any c, right? So then I would have to plug in this value and then say that 5 equals 1 minus 2c, and this fixes my c. So this initial value problem would have only one solution.
Sir, but
Yes.
wouldn't this be equal to minus 1 for any c? Because 1 plus
C
y
equal
equals
to
cx.
cx minus 1. You mean this way?
How?
Okay, I'll change the value. Okay.
Okay.
I can, some by hook or crook, I can always find an initial value problem such that this property is true. Okay, I might make 1,000 algebra mistakes, but my point remains the same. Fair enough? You can
Yes,
your own examples if you want. So there is, try to find examples where you could, in principle, have multiple solutions. It is certainly doable. And you can find many examples in your textbook also. Any questions about these three? So there is actually another example in your textbook itself where they give you an equation like this. Okay. Now, without looking at initial values, can someone tell me what the solution of this differential equation is? The
Y
differential
equals to
equation
0.
is, huh?
Y equals to 0.
Y equals 0, right? Why? Because you have a manifestly positive quantity on the left equals negative times manifestly positive quantity. So the only way a positive quantity equals a negative quantity is if the quantity is 0, right? But suppose if I plug in my initial condition is y of 0 equals 10, then this initial value problem has no solution. If my initial condition was such that y of 0 equals 0, then I can at least write down one trivial solution. Y is just a constant and the constant value is 0 everywhere, right? But if this is my initial value, even that solution is not admissible. So this equation has no solution. This IVP has no solution. So you see, even a simple class of differential equations like first order differential equations can exhibit certain properties. That it could have just one solution, it could have multiple solutions, it could have no solutions. So the question is, what is the condition for these varying cases? So these go by two theorems, and I will not prove the theorems. And these theorems are basically sufficient conditions, not even necessary conditions. But once you satisfy these two theorems, you can be guaranteed that most of everything that you see is probably is covered. So what are the two theorems that I'm talking about? The first question that you can ask is, what is the condition under which there is a solution for a differential equation? Okay, this is the question of existence. Existence. This means what are the conditions for a given IVP to have at least one solution. Okay. Which means that this could be more than one solution. I just want the condition that at least one solution exists. The second question that you can ask is uniqueness. What are the conditions for, excuse me, a given IVP to have at most one solution? Okay. The second condition is, what is the condition? The second question is, what is the condition that a given initial value problem has only one solution? In other words, the solution is unique. Okay. So let us look at the existence first. And it turns out that the theorems themselves are quite simple to state, even though we will not prove them in this class. The first goes by the name of existence theorem. These theorems are due to a mathematician called Picard. And I will simply tell you what this theorem means. So let us say that you have a differential equation of the form y prime equals f of xy. Okay, remember that this is the explicit form of the differential equation. I can also have some function of y prime, y and x equals 0, but it's usually stated in this explicit form. So let me take this explicit form. Y prime equals f of xy. And since I want an initial value problem, let me say that my initial value condition is y at the point x0 equals y0. This is my initial value. The question is, what are the conditions under which there is at least one solution for this differential, for this initial value problem? And the answer is provided by the simple statement that simply look at the right-hand side of this differential equation, the function f of xy. Okay. And if this function f of xy around the initial point x0, y0, around the initial value that you have x0, y0, in the neighborhood of the initial of the points x0, y0, if this function is continuous and bounded, then you are guaranteed that at least one solution exists. Okay, there could be many more. It doesn't tell you how many more or anything like that. The value of this theorem is a little restricted, but it tells you that as long as this function f of xy is continuous and bounded in the neighborhood of x0, y0. So f of xy is continuous and bounded in, excuse me, in the neighborhood of x0, y0. Okay, so I should define what I mean by in the neighborhood. That's why I've put this under quotation marks. But if this condition is satisfied, this is all you have to check. Given an initial value problem, if somebody asks you if a solution exists, simply check if the f of xy is continuous and bounded. Okay, what is continuous? Continuous, as you guys know from your calculus classes, simply means that, you know, if you approach a point from the left and the right, you get the exact same value for the function at the point. Let us say if this point is C, then the left derivative and the right derivative at the point is the same. F prime of C is the same, whether you approach the point from the left or the right. And it bounded simply means that this function cannot have any asymptotes in the neighborhood, right? It cannot blow up. If something blows up, then around that point, it is not continuous anymore. So you have to check for boundedness and continuous in the neighborhood. So what is the neighborhood? So let me define this a little more carefully. The way you define this is you look at the point x0, y0 in the xy plane. So let me draw the xy plane. So this is my y and this is my x. Okay. Now let me draw a rectangle around the point x0, y0. Okay. Now, since I'm very bad at drawing stuff, I will first draw the rectangle and then mark the point. Even then I get it bad. Okay. So this is the point x0, y0. Okay. And then around this point, I'm drawing a rectangle. So let me be more precise. This is x0. This is y0. And the sides of this rectangle are a and b. or 2a and 2b. So this is the point x0 minus a. This is the point x0 plus a, y0 minus b, and y0 plus b. Okay, let me call this rectangle some r. So I'm considering a region R, which is defined by x minus x0 is less than or equal to a, and y minus y0 is less than or equal to b. Okay, the theorem says that if f of xy is continuous in R and bounded such that the absolute value of xy is less than or equal to some value k for all xy belonging to R, then a solution exists. A solution exists, at least a solution. Then at least one solution exists. Okay. And at this point, you should ask where. Now, remember that A and B at this point are arbitrary, right? So I can now make this A as big as possible and B as big as possible and basically cover the entire XY plane and say that, oh, solution exists everywhere. Now, that will be not possible in general, right? So as I said, the reach of this theorem is more limited. Ideally, it'll be nice if you have a theorem that tells you if a solution exists anywhere in the XY plane, but this theorem only talks about the neighborhood of the initial value point. So then how do I ensure that I'm only talking about the neighborhood of the initial value point? This is what the theorem states explicitly. At least one solution exists in the subregion x minus x0 is less than or equal to alpha, some number alpha, where alpha is smaller of a and b over k. In other words, simply increasing and decreasing b or whatever it is does not help you. The region around which whether or not a solution exists is given by the differential equation itself. We will look at an example where this will become clear. In general, simply making R as big as possible won't really help you, because a solution might not exist in the entire region of R. Usually it can maybe only exist in a region like this. Let us say, I don't know, where this is x0, this is, excuse me. Oops. This is x0 minus alpha, and this is x0 plus alpha. Now, alpha could be as big as A itself. If you chose the rectangle carefully, right? If you looked at your differential equation and you chose the rectangle carefully, then alpha could be as big as A. But in general, it could, in many cases, it could be even much smaller than A if you did not choose the rectangle carefully. So all this theorem tells you is that there is some neighborhood around x0, y0 in which a solution exists. So what does this theorem mean? And what is this A and B over K? So let us try to understand what this means. When I say that f of xy is bounded, I mean the following. So since my differential equation is y equals f of xy, when I say f of xy is bounded, I mean that y prime is bounded. In other words, if you write down a solution for this differential equation and you figure out the slope of this solution curve at some point x0, y0, then the slope cannot be arbitrarily large. Since f of xy is bounded, the slope is bounded, right? Slope is less than or equal to k. So let's draw the rectangle again and explain what these two numbers a and b over k really mean. Okay. Again, you have to depend on my drawing skills, unfortunately. But your book does a much better job at showing this. Okay. So let me say that this is the point x0, y0, and I have some solution curve that passes. I don't know what, some y of x that is solving this differential equation. Now, slope, absolute value of slope being less than or equal to k simply means that the value of slope at that point can at most be equal to plus k or minus k. So let's draw two lines, one with slope plus k and one with slope minus k. These are the hopefully similar looking lines. And this has slope plus k and this has slope minus k. Okay. So now what is the actual value of slope? So let us look at this. Right. So this entire thing from here to here is b, right? So slope in this case is k. And this is equal to this distance divided by this distance. Now this x distance is of course a, but the y distance is less than a. Right? So let me call this y distance as some q times b, where q is some number less than 1. So k is qb over a. Does this make sense? Is my diagram okay? All I'm saying is that since a slope is bounded, and I'm simply figuring out what the slope is, there is basically only two cases. The slope can be plus k or minus k. This is the maximal allowed case. Okay, it can be something lower than that, in which case my q is correspondingly smaller. So I'm looking at the maximum case where the slope is equal to k. So this means, what is this number b over k? This number b over k is a over q. And since q in this case is less than 1, so b over k in this case is greater than a. So if this is the case, if you consider any slope such that b over k is greater than a, then since b over k turns out to be greater than a, the validity, the solution exists in some region between x0 minus a and x0 plus a. So remember that the theorem guarantees that the solution exists in x0 minus x minus x0 is less than alpha, where alpha is the smaller of the two numbers a and b over k. So this is the case where b over k is greater than a. So the solution is actually guaranteed to exist in the actual chosen rectangle. So you're actually good. You chose the rectangle carefully. But suppose if you choose the rectangle incorrectly, what do I mean? So suppose if you choose the rectangle like this, okay, again, so this is some, so let us say that this is your x0, y0, and this line is plus k, and this line is minus k, or whatever it is, right? So in this case, again, what is the slope in this case? So again, there is a solution curve that passes through this point, and the slope, which again I take to be k, equals the y-axis. The y distance is of course the entire distance b, but the x distance is smaller than a. So I'll choose a times q, where q is some number smaller than 1. Now in this case, b over k is a times q, which is smaller than a. Okay, so if you chose the rectangle this way, and if your slope turns out to satisfy this property, that b over k is smaller than a, then the region of validity of the solution, or the possible existence of the solution, is not guaranteed in your entire rectangle from a to b. It is only guaranteed from x0 minus b over k to x0 plus b over k, because b over k turns out to be smaller than k. So the choice of a rectangle cannot be arbitrary. You cannot take any big rectangle and claim that a solution exists somewhere in this rectangle, because that will be too arbitrary. The theorem is a little more restrictive. It simply says that, look, there can be only some small region around x0, y0 in which a solution can possibly exist, because your initial value problem is only defined at x0, y0. And the way you figure out this particular region is by choosing the rectangle carefully. Okay. Now let me move over to the second question of uniqueness, and then we will look at one example. So I call this existence theorem. So I'll call this uniqueness theorem. Again, take the same rectangle, take the point x0, y0. So again, I will write the same differential equation with the initial condition y of x0 equals y0, right? Same rectangle R, x minus x0 is less than or equal to a, y minus y0 is less than or equal to b. And now we are asking a slightly more involved question. We are saying, look, what is the condition that I have only one solution? Okay, the condition that there is only one solution is given by the following two conditions. Look at the boundedness of f, right? So I'm assuming the partial derivative of f with respect to y is continuous in this region. So the conditions that have to be satisfied are f of x, x comma y, as usual, remains bounded. But in addition to that, the partial derivative of f with respect to y also remains bounded for all x, y in R. Okay. So obviously, since uniqueness is a more stronger constraint, you would have additional conditions. The additional condition is a condition on the derivative of f with respect to y. If this is satisfied, then the solution is actually unique. Okay. So let us actually look at one of the two examples that we discussed and check if it makes sense. So let me take y prime equals, I don't know what it is, x times square root of y minus 5, right? So f of x comma y in this case is x times square root of y minus 5, right? So let us look at the first initial value problem. What was this? x0, y0 was 0, 10. Okay. So is the solution continuous around this point? Obviously, there is nothing wrong with the solution, right? So x is a perfectly valid function and the square root of y is a perfectly valid function. So square root of y minus 5, of course, starts at y equal to 5 and goes something like this. So everything is continuous. There is no problem around the point 0, comma 10, right? What happens to df dy? What is df dy? This is 1 over 2x square root of y minus 5, right? Now, is this function continuous at, sorry, this is partial derivative of y with respect to x. So the x remains on top, right? X is equal to 0. This function is 0, no problem. At y equals 10, this is some square root of 10 minus 5, whatever it is. This is a perfectly continuous function around the point 0, comma 10, right? So is the function bounded? Well, take some rectangle and ask yourself if the function is bounded in this rectangle, and you would actually find that this is also satisfied. So this function is continuous, its first derivative is continuous, and things are also bounded. So I can expect a unique solution for the initial value problem, x0, y0 is 0, comma 10. So which is why we could figure out a unique solution with a unique c, where c was equal to 2 times square root of 5. Right? So take the same thing and look at the, I don't know what I should call this, I'll call this 1. And let's look at the same thing, but with the second initial value problem. In fact, I will, okay. X times square root of y minus 5, okay? And this time the initial value is 8 and 5. Again, there is absolutely no problem with the continuity, right? So f of x comma y is x times square root of y minus 5. And around the point x0, y0, of course, f is 0, but 0 is a perfectly okay number. So this is fine. It is certainly continuous. But df dy, which is x over 2 square root of y minus 5, asymptotes at this point, right? So remember that this is a very bad behavior. So the first condition that the function itself is continuous guarantees that there is at least one solution, possibly more. The second condition that the partial derivative is continuous and bounded guarantees that there is only one solution. So for this particular example, it is certainly guaranteed that there is a solution because f of xy is continuous. But since the first derivative blows up, the second uniqueness theorem is not satisfied. So this solution is bound to be non-unique. This is unique. Okay. So this is how practically you test whether uniqueness is true or not. And there are cases where you can test quite easily, like in this example, where a given initial value problem has a unique solution or not a unique solution. Okay. So now let us look at, yes.
Just want to confirm one thing. Unique solution means that equation will have just one solution, is it?
Correct. Unique solution means that there is the given initial value problem has only one solution. A solution exists and there is only one of them. There is nothing else possible.
Okay. Okay.
So in the first case, this was unique because there was only one value of c and there was no other solution possible. The second case, if you remember, this is non-unique because I could write one value of c, but I could also write a constant function f equals 5, right? So there's more than one possible. So it is certainly not unique. This initial value problem is certainly not unique.
Okay.
There could be more non-trivial examples also. So this is an example from your textbook, which is actually quite illustrative. So y prime equals 1 plus y square. So let us look at the construction of the rectangle, right? So f of x comma y, of course, you can directly solve for this and the solution is tan, but that is not the point. Let us look at this function 1 plus y square. Okay. And let us take some rectangle where I choose a to be 5 and b to be 3. So I'm drawing a rectangle and my initial, so I should first specify the initial value, right? So otherwise it doesn't make sense. So y of 0 equals 1. Now for this initial value problem, if I construct a rectangle such that A equals 5 and B equals 3, and now I ask myself, if in this rectangle around the point 0, 1, can I make the claim that a solution exists somewhere in this region? So let us check. So what are the conditions for uniqueness? The conditions for, the condition for existence is that it is continuous, and the continuous is easy to check, but let us actually go ahead and look at the boundedness also. So in this case, I want f to be less than or equal to some value of k. Now, what is since f is 1 plus y square, what is the maximum value of k that I can have? Well, the maximum value of k corresponds to the maximum value of y inside this triangle. The maximum value of y inside this triangle is 3, because that is the maximum value of 3. So f of xy should be less than or equal to k, and k in this case turns out to be 10. What is df dy? Df dy in this case is 2y. So df dy, we claimed for uniqueness, has to be less than or equal to some m. And in this case, m turns out to be 2y, and 2 times 3 is 6. Okay. Remember that if this was a function of x and y, to take the maximum value, I should plug in the maximum value of x and the maximum value of y. This is a very simple problem in which you can directly do this. Okay. So now the question is my entire, excuse me?
How did we get k as 10?
So my rectangle is this, right? So in this case, so this is the point x0, y0, which is 0, 1, right, in the xy plane. Agreed? So I am choosing this, right? I am choosing a equals 5 and b equals 3. I don't know. I can choose other things also. A equals 10 and b equals 5. I need to check, right? So where my solution possibly is, where in the xy plane is my solution guaranteed to exist? So suppose if I choose this particular value of a and b, then the maximum value of x in this rectangle is x0 minus a to x0 plus a, right? So this is my x0, and x0 is of course in this case 0. So this is minus 5 to plus 5, right? And the distance b is 3. So this is 1. So this is 1 plus 4 to 1 minus 4. So this is my rectangle, right?
Yeah.
So the maximum value of y is 4 inside this rectangle, right? Sorry, 3 inside this rectangle, the distance, actual distance. Right? So this length is 3, right? 3 units, whatever it is. Make sense?
Yeah.
Okay. So this sets my maximum value of k and maximum value of y. So now the question is, can I claim that the solution exists anywhere inside this rectangle? Well, let us check. A is 5. So, and what is b over k? Excuse me, wrong color. B over k is actually, b is 3 and k is 10. So this is 0.3. Now remember that the theorem guarantees that the solution exists, right? And the existence region is x0 minus alpha. Sorry, x0 minus a is less than, what am I writing? The solution region is x minus x0 is less than or equal to alpha, and alpha is the smaller of a or b over k. So in this case, we chose a, but we were being a little too ambitious. We cannot claim that a solution exists anywhere between x0 minus 5 and x0 plus 5. It turns out that in this example, a solution can only exist around x equal to 0.3. Okay, something very small like that.
So I still don't understand why k is equal to 10. K is supposed to be the slope, right?
Correct. So what is the slope? Slope is dy dx, right? See, let us say there is some solution curve that passes through this point, right? Sorry. Right?
Yeah.
What is y prime at the point x, x0, y0? Y prime is the slope, right? This y of x is a solution. Y prime is the slope. Agreed?
Yeah.
So what is the differential equation? The differential equation is y prime equals 1 plus y square. In other words, slope equals 1 plus y square at some point x comma y. Agreed?
Yeah.
So if I claim that the function on the right-hand side, 1 plus y square is bounded, what I'm claiming is that the slope at that point is also bounded. Because
Yeah.
the slope is the function. That is the differential equation, right?
Yeah.
Now, for example, I could have a more complicated differential equation like y prime equals some non-linear stuff, y prime square equals blah, 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 right? In that case, of course, I cannot make this simple claim. But in this case, since I'm only considering differential equations of the form y prime equals 1 plus y square, I'm basically saying the slope is bounded in some region of xy. Okay?
Yeah.
Is that okay?
Yeah.
All right. So this is how you practically test the region of existence of the solution. In this case, of course, the solution does not exist between x is equal to minus x0 minus 5 and x0 plus 5. It only exists between x0, x minus 0.3 to x plus 0.3. Okay. In this small window, there is some solution. That is all the theorem guarantees. Okay. Now I told you that these are sufficient conditions and not necessary conditions. So these are both called Picard's theorems, in case you want to know the name. It turns out that one can write down a slightly modified version of the second uniqueness theorem. The uniqueness theorem tells you that df dy has to be bounded. But remember from your calculus, the mean value theorem. Okay, what is the mean value theorem in one dimension? Does anyone remember? So let us say that you have some function f of x, right? And let us say that there is 2 points A and B. Okay, and let us say that this function is perfectly continuous and well behaved in the interval between A and B. Then the mean value theorem says that there exists a point C between A and B so such that A, where it is C less than such that f of B minus f of A equals, does anyone remember now? The derivative of the function at the point C is simply related to the values of the function at the two endpoints divided by the interval. Okay, it looks like a definition of derivative, but it is not quite, because B and A need not be infinitesimally close. So this is a mean value theorem of calculus, and I can use the mean value theorem to write a slightly modified version. So instead of saying df dy is less than or equal to, what did I call it, some value m, I can use the mean value theorem in y. So I can claim that this function f is such that f of x comma y2 minus f of x comma y1 equals y2 minus y1 times df by dy at some point y tilde, where y tilde is between y1 and y2. This is the mean value theorem in action. This is the exact same statement as this, except that in this case, the function is a function of two variables and not one variable. I have written down the mean value theorem for the variable y. Now remember that uniqueness theorem puts a bound on the absolute value of the derivative. I can turn this condition into a slightly different modified condition by claiming that this simply means that f of x comma y2 minus f of x comma y1, this difference in the value of functions is now bounded by y2 minus y1 times m. Because the derivative is bounded by m, I can claim that this difference in the value of functions between y2 and y1 is now bounded by this particular quantity, y2 minus y1 absolute modulus times m. Okay. It turns out that this is also easy to test, and it's a slightly weaker condition, and this condition is called the Lipschitz condition. If I get the spelling right, this is what it looks like. Okay. So you can either test for continuous derivative, boundedness of the partial derivative itself, or you can simply test for the Lipschitz condition. They can both give you the correct answer. So I will work out the example that is given in your text and stop. This is a simple example, so it shouldn't take me too long. So the example is this. And my initial condition is y of 0 equals 1 or something like that. Or y of 0 equals 0. Now we can solve this differential equation. The way you solve it is simply put y equals u equals y square, like in the Bernoulli problem, and then you can solve this equation. And it turns out that you can have two different solutions. So y equals 0 is actually a solution. And then y equals x square over 4 in the positive x-axis and minus x square over 4 in the negative x-axis. Okay. So why is this necessary? This is necessary because f of xy is square root of modulus of y. Okay. So remember that y prime in regions less than x by this definition turns out to be positive. Okay, because y prime is x over 2 for x greater than or equal to 0 and minus x over 2 for x less than or equal to 0. If I simply had x square over 4 everywhere, then my y prime would be negative for negative x. I don't want that because y prime is a manifestly positive function. So I should have this particular solution. Okay, so this is how we understand the solution. And f of xy in this case is perfectly continuous. It is square root of y. Okay, so I can guarantee that a solution exists around x is equal to 0. Sorry, 0, 0. Okay, but is it unique? Obviously, it is not, because I'm having all these different kinds of solution. And the way you do this is by testing the Lipschitz condition. So Lipschitz condition tells you, you can test for the derivative, but let us test for the Lipschitz condition. So in this case, f is square root of y. So let's take 2 points. y1 equals 0 and y2 equals some value y2. Okay, and now let's check the Lipschitz condition. What is this? This is square root of y2 minus 0 divided by y2 minus y1 is less than or equal to some m, right? So in other words, the left-hand side should be bounded by m. That's what Lipschitz condition states in order to have a unique solution. But what is the left-hand side? The left-hand side is 1 over square root of y2. And what is y2? Well, y2 is in your hands. If I make y2 quite large, then of course this bound will be satisfied, because 1 over square root of y2 will be small, but nobody said I should make it large. Right? I can also make it as small as I want, in which case I can violate this condition. So there is no guarantee that a solution is unique, because I can always choose my y2 such that the Lipschitz condition is violated in this case. And that's why you have multiple solutions. A solution exists, but its uniqueness is not guaranteed. Okay, so this is another example where the initial value problem has a non-unique solution. Okay, so the lesson to learn from this is that test for the continuity of the function and the boundedness of the function, and then you can be guaranteed that a solution exists in some interval. To figure out this interval, draw the rectangle and then figure out the values of a and b over k and compare them. Whichever is smaller is the region of validity of the solution. To test for uniqueness, take the partial derivative of the function with respect to y and test for its continuity and boundedness, or equivalently check for the Lipschitz condition. Okay, see, these are the 2 to 4 simple steps that you have to follow to check for existence and uniqueness in the case of first order differential equations. You can also check for these in the higher order differential equations that we will talk about when we talk about second order differential equations. Okay, so that will be the subject of the next lecture. So I'll stop here, and then we will see each other again on Thursday. Okay, any quick questions before we close? Quick questions or comments? Is all of this material okay? All right.